Hi all, this is Alan with Bothell STEM Coach, and today we're going to be wrapping up the AP Physics C, E, and M free response questions, and this is the set 1 of the questions, by the way. Look for look on my channel for the videos if you're looking for the set 2 questions. And as usual, if I have any mistakes and I need to make any corrections, they'll be in the description below, as well as links to the PDF solutions are in the link in the description below. So a solenoid is used to generate a magnetic field. The solenoid has an inner radius A, length L, and N total turns of wire. A power supply not shown is connected to the solenoid and generates a current I, shown in the figure of the left above. The x-axis runs along the axis of the solenoid and generates a current I, shown in the figure in the left above. Point P is in the middle of the solenoid. It shows a cutaway. Okay. State the correct direction of the magnetic field at point P. So you got to kind of have to like do your right hand rule. Thumb is sort of like in the direction of the current. And you got to look at your coil. As I go around the coil kind of into the page like this, basically my fingers are always like, going to the right. And so it's going to be going this direction here, the B field. So positive X direction. And right hand rule. I don't know what the justification. Just a little bit of explanation of what you just described. On the cutaway view below, clearly draw an Amperian loop that can be used to determine the magnetic field at point B at the center of the solenoid. Okay, so this is like a standard derivation, but in case you didn't know, like you're gonna, because everything is going in the right direction and to the right, you kind of want the loop to go like this. And then you're going to make a rectangular loop. Now, this is weird because what you do is typically with this part of the loop, you make it extend to like really far to where the magnetic field is 0. But I can't like draw this infinitely big, I guess. So just say it extends forever in that direction. Use Amperes Law to derive an expression for the magnetic field at point P. So the way this works is, Amperes Law is the line integral of B dot dl is equal to mu naught I. Now, fortunately, we can break this into 4 segments. Like when I do this line integral, it's 1, 2, 3, 4. So I'm going to label them 1, 2, 3, and 4. Now, in segment 1 is sort of where there's a magnetic field. So if I look at section 1, the magnetic field, if I make this kind of thin enough, like the width of the imp is like really far away from the ends, and it sort of, we assume it's constant over this length. This evaluation, B dot dl, would just be equal to B times the length. So let's derive let's explain some parameters of this loop. Let's say delta x is sort of the delta x like that. And let me just make sure I have the x direction. Yeah, x is that direction. And then so B dot delta x is this portion of the line integral. Now sections 2 and 4, this line integral is 0. And it's 0 because along these points, the magnetic field is horizontal. Okay. So we're saying there's no perpendicular portion of it. And the reason there's no perpendicular portion, I don't know. It's just sort of a property of the solenoid. But basically, the magnetic field, it escapes me right now why we think that the magnetic field has no vertical component here. But if it did, by symmetry, it would cancel out on this side. Okay? Because say it had a little bit of a vertical component, which it doesn't, but say it did, it would have to be like symmetric, I think, on this side also. And so when I do my line integral, they would just cancel each other out. Anyway, so 2 and 4, but it's simpler to just simply say they have a horizontal component and they cancel each other. They're 0 when I integrate. Like the B is perpendicular to my direction, so this part is 0. Now segment 3, I make far enough away that I say the magnetic field is 0 because it's far enough away. Okay. All right, good. So let's see. So now we go back to Amperes Law. The left hand part is equal to simply B times delta x. That's what we found. And now this is equal to mu naught times the current enclosed by the loop. Well, there's n total turns, right, over L. So that means like the ratio of the number of turns is delta x over L times n. Okay, because delta x over L is sort of the fraction of the length of the entire solenoid. And so that fraction times the total number of turns is how many turns are just right in here. So it's that many turns times I. Because the current is going through that loop multiple times, however many turns it goes through, right? Okay, so the delta x's cancel, and so I get B is equal to mu naught Ni over L. And I think they give it to you in this as an equation sheet. Typically it's written as like with a little n, I over little n, where n is equal to L over n. This is the standard equation you would find. So this matches, right? So we got the right answer at least. So some physics students conduct an experiment to determine the resistance Rs of a solenoid with radius A equals 0.015 meters and a total turns N equals 100 and a total length L equals 0.4 meters. The students connect the solenoid to a variable power supply. A magnetic field sensor is used to measure the magnetic field strength along the central axis of the solenoid. A plot of the magnetic field strength as a function of the voltage of the power supply is shown above. Okay. So first draw a line of best fit. And if you guys have watched enough of my videos, I'm not super great at this, but I will do my best. We'll call that my line of best fit. That's not bad. Not too bad. Okay. Maybe, yeah, no, I like it. Use a straight line to determine the resistance Rs. So, first of all, let's sort of derive what Rs is. It's sort of like useful to magnetic field strength. So we measure the magnetic field. And so what was our equation we used? The equation was mu naught Ni over L. And if you weren't able to derive with Amperes Law, you could have used the equation from the equation sheet. I think it's just to point out the equation sheet. I just want to like point it out in case you were curious. It looks like it is this one here. Yeah, magnetic field of a solenoid. Oh, it's N times I. Yeah, sorry. I think I had the mixed up there. But do I have these units right? Let me just make sure. Now that I look at that equation, I want to double check. N over L times I. Let me check my solutions. Just double check. Yeah. Oh, this is supposed to be a lowercase l, not a capital. I was doing that in the solutions too. I don't know why. Like in my mind, I just use a capital L. But okay. Okay. So let's see. This is right. And so what are we doing is we're applying a voltage. So the current generated is equal to the voltage applied divided by Rs, right? So this equation then becomes mu naught N over L V over Rs. And so what are we plotting is we're plotting voltage on the x-axis and B on the y-axis. So my slope, if I bring out the V, is mu naught N over L 1 over Rs. This is my slope. This is slope right here. So I'm going to calculate this slope and then back calculate what Rs is given a slope. So let's pick some points. I like this point here. I love it when they plot the data for you. I hate figuring out the actual like the grid and doing all that. I just find it really tedious. Okay, important but tedious. So this is 7.5. So this point is in the y direction. It is 2.678. What's that? 2.8 times 10 to the minus 4 minus this y value is we'll call that 0.6. 0.6 times 10 to the minus 4 divided by the x value here, we said was 7.5 volts. I'm not writing units. Minus 1 volt. Okay. 2.8 minus 0.6 divided by 6.5 is 0.338 times 10 to the minus 4. Now that's my slope. And that has to equal mu naught n over L, 1 over Rs. So Rs is going to equal, I'm going to bring Rs up here, bring this on here. It's going to be mu naught n over L times 0.338 times 10 to the minus 4. And this is 4 pi times 10 to the minus 7, I believe. Let me just double check that. Yeah. Number of turns they gave you was 100, I believe. Let's double check that. 100, and length was 0.4. You might notice that my PDF solutions have slightly different, because I always rederive these, and so the numbers might be a little bit different because depending on the way I drew it. So times 100 divided by 0.4, then divided by 0.338 e minus 4. I get Rs is 9.3 ohms. Call it 9.3. And that was a pretty big difference from what I had before, so I just want to double check 338. And before I had 381, so I don't know. Like I picked slightly different numbers and my slope was a little different before. That's fine. One of the students note that the horizontal component of the magnetic field is 2.5 times 10 to the minus 5 Tesla. Is there evidence from the graph that the horizontal orientation of the solenoid affects the measured values for B? Yes, I have a y-intercept here. Because 2.5 times would be 0.25 times 10 to the minus 4, and 0.25 times 10 to the minus 4 is right about there. Hey, that's pretty good on that. So, that's I drew it right through that point without even trying. But yeah, it looks like it is. Would the horizontal orientation of the solenoid affect the calculated value for Rs? No, because the slope wouldn't change, right? Our calculated value for Rs came from the slope, and if you just shift the line vertically, which is what the presence of the Earth's magnetic field would do, I just shift everything up vertically, the slope would still be the same. So it really wouldn't affect our answer. Okay, so then we have a thin conducting loop of radius R of B and resistance RL is placed concentric with the solenoid as shown above. The current in the solenoid is decreased from I to 0 over time delta t. Is the direction induced in the loop clockwise or counterclockwise during the period? Okay, so here we're going to use, so far right now what's happening is I have a magnetic field through here, right? But it starts decreasing. So the magnetic field is the flux is going to decrease. So the magnetic field through here is weakening. So the induced current is going to want to create a magnetic field through the center in order to compensate for the decrease in the magnetic field flux, right? It's going to be like, whoa, 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 my magnetic field is decreasing. I need to create a current that will create a magnetic field. And to do that, using your right-hand rule, it's going to be clockwise. A clockwise current would then create a magnetic field that goes to the right in the center. Derive an equation for the average induced current in the loop during the time period that the solenoid is decreasing. Express your answers in terms of all of this. Okay, so in general, you usually want to start with the voltage. The voltage is the negative derivative of the flux over time, right? So let's calculate what the flux is. The flux through what is changing? So the flux, if I assume that the magnetic field is, what did I do here? I said it was just B times the area. What is the flux? So the magnetic field through a solenoid is constant throughout here. So if I have my loop, I might have derived this incorrectly in my solutions, so I'm computing the flux. What is the flux? So I know the magnetic field through the lines through this portion. Question is there any magnetic field outside of the solenoid? And would I need to add that up? Let me derive it real quick, if you give me a moment. I know the magnetic field here is inside here, it would be 0 because if I did an ampere loop, you know how it goes to infinity, and I said I calculated out here that this had no contribution of my Ampere law. But if I bring this thing down and this part is still the same and I'm still enclosing the same current, the magnetic field here and here have to be the same because the contribution of the line integral for Ampere's law would be the same. So I did this right. There is no magnetic field going in this direction, or it's negligible. It's not that there's none, but it's pretty negligible. So the flux is just B times A. I know the strength of the magnetic field. It is mu naught I. Mu naught I. Mu naught Ni over L. Yeah. And then the area is the area of this circle right here, which is pi times A squared. Okay, so that is VB. So all of these are constant. Mu naught N pi A squared over L times I. I is the only thing that's going to start changing, right? So when I take the derivative of this, negative derivative of this, I is just changing. So it's mu naught N pi A squared over L. And this would be the change in I over the time it takes. Now the change in I is to go from I all the way down to 0. So it's 0 minus I, which is negative I, right, over this time. So this negative I cancels with that negative. So the voltage induced would be positive mu naught N pi A squared over L times I over delta T. Now that's the voltage. They actually want the induced current. And I have to divide the voltage by the resistance of the loop, right? V over R L. So mu naught N pi A squared I over RL L delta T. Ooh, that was a lot of variables in there. So, all right. Let me know how you did in the comments below, or if you noticed any mistakes I made, or if you have any questions, and I'll see you next time.